How many of you are first years?
All used.
Okay, nice. Target audience is here. So this is the topic of our talk. All roads lead to the Supremum, whatever. So yeah, what Mukil asked, I'm gonna start a little bit different. Do you guys know what a real number is? Like, what is the set of real numbers? How will you describe?
The numbers which can be represented on a number line.
Or anything else?
We studied about Diddy-Kind-Curves. They can be a supremum of a Diddy-Kind-Curves or rationals.
Okay.
There's something else, Cauchy, something like this kind of thing.
Okay, so most of you might have heard about this. Real numbers are complete ordered field. Have you heard that?
Yes. Yeah.
Yeah. So what do we mean by that? Do you guys know what a field is?
Yes. Yes.
So yeah, I'm not gonna take much of your time. Okay. So field is something, it has two operations. It is closed under those two operations. And also like commutative, associative, distributive, whatever. Right? And it has its inverse and all. So what do you mean by ordered field?
A field which has total order, basically two order. There is an order relation. There is a transitivity in the relation.
Basically, it follows the law of trichotomy.
Yeah,
If I'm saying two numbers are in the field, either this is going to be like happening this or this. Yeah. It's fine, right? So now what do we mean by complete? Okay, we're going to discuss about that now. So like from what you have learned, like you've learned about this axiom of completeness. What he said, like if there is a subset of real numbers and that subset is bounded, then it will have a supreme. That's what you've learned, right? It is an axiom, right? The goal of this talk is we are going to use axiom of completeness to prove monotone convergence theorem, and we are going to use monotone convergence theorem to prove Bolzano, and then Cauchy. And what I'm trying to do is do something about it and like basically show that all of them are equivalent. So using Cauchy, I'm gonna show that you can prove axiom of completeness. Axiom of completeness. Okay, so all of them are equivalent.
But wouldn't that be circular logic?
Yeah.
Because all these are coming from the axiom.
Yeah, that's why that's the main thing, right? We can use any one of them and take them as the axiom.
Okay.
Yeah, we're gonna discuss about it more later. So what is axiom of completeness? We discussed, right? This is the axiom of completeness. Now, you guys have learned monotone convergence theorem, right?
Yes.
So, monotone convergence theorem. Alright. Monotone convergence theorem says that if a sequence is monotone, it converges if and only if it is bound. Right? Any doubts here? This like make sense to you guys? So now we're gonna prove it. Okay? Okay. We're gonna take a sequence which is monotone and monotone increasing. We are just gonna prove it for increasing. The similar argument is gonna hold for decreasing, right? Right. So it is bounded above. By axiom of completeness, we can say that it has a supremum, right? It is bounded, so it is also bounded above. And if it's bounded above, it will have a supremum. Now, after that, okay. Now what I'm saying is, if I take any epsilon, which is greater than 0, I can say that this thing is not an upper bound, because I like supremum means that anything less than that is not an upper bound, right? So what we are saying is there will exist some n such that an is greater than a minus epsilon. So Does this line make sense to you guys? Any doubts? So we also have the fact that this is a monotone increasing sequence, right? So we can say this is true, this is true, and so on, right? And all of this is smaller than this alpha, right? So what I'm trying to say here is for all n greater than n, an is between these two things. Does this line make sense to you guys? So we're gonna do some work here, and what we get is an minus epsilon. What does this mean? It converges. Yeah. So what we proved is if a sequence is monotone and it is bounded, then we can say that it converges. Any doubts here? Okay, this talk might be a little boring because at the end of the day we are just proving four theorems, right? But I think like the result it gives us is pretty interesting. Okay, so like the next thing is we're gonna use monotone convergence theorem to prove Bolzano. But before that, we just need to prove a lemma. And the lemma is every sequence in R will have a monotone subsequence. Okay, for this I'm gonna define something called a peak. Okay. What I mean by peak is, okay, suppose there is this sequence, right? Okay, something like this. This is an, this is an plus 1, whatever, right? It goes on. We call something peak if everything after this, like this an, every element of the sequence after this an is smaller than or equal to the an. Okay, so this will be a peak, this will be a peak because everything after that is smaller than, right? Okay, any doubts regarding peak? So now that I've defined like peak, we can only have two cases, right? The number of peaks will be either finite or infinite. No other case is possible, right? Okay. So let's consider the first case. If we say there are infinite peaks, then peak will occur at n1, n2, and like infinitely many times, right? And by the definition of peak, let's say this is the first peak, right? Really. Okay. And it will be greater than or equal to this, the next peak, right? And this will go on, right? So what we actually got here was a monotone decreasing subsequence, right? So if we have infinitely many peaks, then what we get is a monotone decreasing sequence. Now suppose if the peaks are finite, okay, so if the peaks are finite, then there will be a last peak. Does that make sense? So we're gonna name it whatever, like n, like an is the last peak. So there, if it is not a peak, there will exist some n1 which is greater than an, right? So that we have an, and then we have some an plus an1 which is greater than the given an, right? And since this thing can also not be peak, there will exist some a and 2, which will be greater than this. Right? This argument will hold on and we'll get an increasing subset. Right? So what we got was, huh?
Will AN1 be greater than equal to AN? AN is the peak, so
It's the last peak.
it's the last peak, so it will be greater than equal to AN1.
Oh.
AN is the last peak.
Oh, sorry.
Yeah. No, that's fine.
Oh, that's fine.
Right.
Sorry. Yeah.
Yeah.
Does that make sense? Okay, so what we got here is, like, doesn't matter how many peaks we have, we definitely have a subsequence which which is monotone. Right? Now we're gonna move to the next thing. So the main theorem, the Bolzano-Weierstrass theorem, is that every bounded sequence in R has a convergent subsequence. Now we have already proven that every sequence will have a bounded subsequence. Right? Sorry. Yeah.
Every bounded sequence will have a monotone subsequence.
Yeah, it is. Yeah, it will. Sorry. Okay. The sequence is bounded, right? And it will have a monotone subsequence. Now what we got here is a subsequence which is bounded and it's monotone. And by monotone convergence theorem, what we can say? It converges. Right? Yeah. Now we have to move to Cauchy criteria. Okay. This might be a little confusing at times. Okay. Let's see the definition of Cauchy first. Okay. For all epsilon greater than 0, there exists an n, and this thing holds. Right? Does anybody have any doubts? So, the theorem is a sequence converges if and only if it's Cauchy. Right? Like this side of the argument is easy, so I'm not gonna waste your time. Like we have, like the main thing we have to show is Cauchy implies constant. Okay. Suppose we have a sequence which is Cauchy, right? What is the definition? For every epsilon, there exists an n, and
xl minus xl, the am is become model less than epsilon
yeah.
for all l greater than k.
Yeah. Now, the first thing I want you to like understand, we are using Bolzano to prove Cauchy, right? So if we are saying we are using Bolzano, then we need a bounded sequence first, right? So our first aim is to prove that every Cauchy sequence is bounded. Okay. So it is true for all epsilon, right? So it will also be true for epsilon is equal to 1. Any doubts? Okay, so for this epsilon, there will exist some n. Does this make sense? So can I also like write it something like this? N plus 1 is greater than n, right? So I'm going to replace m by n plus 1. Okay. Like this argument makes sense, right?
Not if and only.
Hmm?
Not if and only. It will be implies.
Oh, sorry. So now you can write it something like this. Does this line make sense? Now, what we are trying to show is that this thing is bounded, right? So, if I take a set something like this, if I take a set which is the minimum of this, what I'm trying to do here is the minimum element will lie here because till n I've written down every single element, and for all n greater than n, right, we have this thing which is smaller than every single n greater than capital N. Does that make sense? I'm taking the minimum. Just okay. I'm trying to find the minimum, right? Okay. So I've taken every finite elements till this capital N, and have taken this thing which is definitely smaller than every element which is greater than. Any doubts? Or and similarly, I can also have this U, which is the maximum of this. Okay. Now, what I can say is does this line make sense to you? Sure. So the sequence is bounded. Now, what does Bolzano-Weierstrass theorem say? Yes. Right. So there will exist a subsequence A N G such that converges to some point. Right? Okay. Which one? This one? Okay. So I want to say find the what I'm trying to do here is I want to show that every Cauchy sequence is bounded. And if I want to show that something is bounded, I need to find a real number which is smaller than all of the sequence, like all of the elements of the sequence, and a number which is greater than all of the numbers. Right? So what I did here is I have taken every single element, like every single element before this capital N, and I have put it here. And we know that for all n greater than this capital N, this thing is smaller than all that element, those elements, right? So the minimum of the sequence will lie somewhere here only, and the similar argument holds for the maximum thing. So what I got was I found something called an L and a U.
This should not be strict inequality.
So this shows that this sequence is bounded. And if a sequence is bounded by Bolzano-Weierstrass theorem, we say that it has a convergent subsequence. And I have named this subsequence something like this, and it converges to a point A. Okay. Now, I'm just going to write down the definition of Cauchy and the definition of convergence. This is the definition of Cauchy, and this is the definition of a convergent subsequence, which I described here. Right? Any doubts here? Right? I've just written down the definition. Okay. Now, what I'm trying to say here is there. Okay. I'm leaving something called J. Okay. So J is the maximum between N1 and N2. Okay. Now, this argument, the thing that I've written here, will hold for all N, M, and J greater than J, the capital J. Right? Okay. And also something I want you guys to note is right, because we are writing some subsequence, right? So either it can be equal, like okay, A1, A2, AN, whatever. So if I write a subsequence, either it will be 2 or greater than 2 only, right? We can't have something which is smaller, right? Because it is a subsequence. So does this imply this? Okay. Now I'm gonna write for capital J. We have something like this. Saying triangle inequality, we can write it like this. Okay. Now I'm going to use triangle inequality. Now this thing converges to, like, is smaller than epsilon by 2 by the definition of Cauchy sequence, right? And this thing is smaller than epsilon by 2 by the definition of the convergence of sequence. Right? So what we got here is that every Cauchy sequence converges. Right? Okay. Now here is the main part of the talk. We have to close the loop as well. If you want to show that every single of the statements that we have given are equivalent. So the Cauchy criteria itself is not enough for that. We need the Archimedean property as well. And you're going to see that in the proof, where it comes, where it features. So to prove that, like what is the statement of axiom of completeness? That,
If the set is bounded, then there is a solution.
yeah, right. So we are given a set which is bounded above, right? And now we have to show that this set has a supremum, right? Now for that, I'm gonna try to construct a sequence. What I've done here is I've taken an element from A, which is not clearly not an upper bound because we are trying to find, okay? And we have taken an element B, which is an upper bound, right? Because it is bounded above, so it will have an upper bound, right? So now I've constructed the sequence like this. Okay. So the sequence, okay, x1 will be B. Okay. So what I've constructed basically what I've constructed is a sequence of upper bound. Because x1 is an upper bound, right? Because B is an upper bound. We have taken the B to be an upper bound. And what I'm saying is, if I subtract this thing from xn, I'll do that only if and only if this thing still is an upper bound, right? Does that make sense? So the entire sequence is a sequence of upper bounds. Now we have to use Cauchy criteria somewhere, right? So what we'll try to do is we'll try to show that this sequence is Cauchy. Okay. Okay. When you see this sequence, are there any thoughts that come to your mind? Like, what is the first thing you thought when you saw a sequence like this? Like, the first thing is it is a sequence of upper bounds, right? Anything else? Yeah, it is a non-increasing sequence, right?
I mean, it is a decreasing sequence.
Like, I mean,
Exactly, it is a decreasing.
no, I'm saying that if it is not an upper bound, it will stay that xn plus 1 will be xn, right?
Yes, so it is decreasing. Not increasing.
Huh. Okay. Now, the maximum drop you can have in the sequence would be that every time we are able to subtract this thing, right? So, at max, we'll be able to drop this sequence by something like this. This is a geometric series, and this converges to, any ideas? Yeah, converges to 1, right? Does that make sense? So this is the maximum possible drop. So let me take some n which is greater than it. Okay. So since it is a non-increasing sequence, this thing holds, right? Does this make sense?
Not increasing means strictly decreasing or just decreasing?
When I'm saying non-increasing, it might be that like
Equal.
yeah. Now this max drop thing that we discussed, the max drop here can be right. We get to keep subtracting it, okay, and this will be definitely greater than that, right? Now this is also a geometric series, right? So what this is equal to is a basic calculus, right? So what we got here is for all, like for all m and n, this thing will hold, definitely hold, right? Now for for any epsilon, let us take some epsilon, okay? Now using Archimedean property, can I say that there will exist some n such that is, no, this is just, I'm just using Archimedean property. What is the spelling of Archimedean? Nice. Nobody knows. Okay. Oh, nice. Okay. So for n comma n, this like makes sense. So what we got here is that this sequence that we have constructed is Cauchy, right? Any doubts? Now using Cauchy criteria, we can say that this thing will converge, right? Xn converges to some L, right? We are just using the Cauchy criteria. Now, what I claim is that this M will be the supremum of the A that we talked about. Right, the A subset. We need a supremum of that subset, right? So I'm saying that this M will be the supremum. But I just can't say it, right? I have to prove it. Yeah. So for that, how do you prove that something is a supremum? Yeah, exactly. So first we have to show that this is an upper bound. Now, for all A naught belonging to this set A that we talked about earlier, right? We are discussing all of this thing for that set only, right? What I'm saying is that because the sequence we have constructed is a sequence of upper bounds. So for all the things inside this A, they will be less than every element of that sequence. Right? We can say, you know, right? So what we said here is L is an A. Now comes the main thing. We also have to show that this is the least upper bound. Right? Now to prove that this is the least upper bound, what do we do when we don't have any idea of how to prove something? No. No. We just take contradiction, right? Like, you don't understand something, just try to prove it via contradiction. At least that's what I try to do. Okay. So assume L is not the least upper bound. Okay. If that's the case, there will exist some M which is an upper bound such that M is smaller than N. Right? Now we can use this M and say that epsilon is equal to L minus M. This is greater than 0, right? Now for this epsilon, by Archimedean property again, I'm not gonna write its full thing because I don't know how to pull it. Right? You can say that by Archimedean property. Now, this N will give us two cases. Okay, let's go back to the sequence that we were talking about. We were talking about xn, right? So what I'm trying to say is the xn plus 1th term of the sequence will have two choices. It will either dip or it won't. Right? So let's talk about those two cases. Xn plus 1 is equal to xn. Okay. If that's the case, what we say is that xn minus is not an upper bound. Right? That's why we will get no this is equal to. Now, if that's the case, if this is not an upper bound, there exists some A naught belongs to A such that A naught is greater than Does this make sense? Now, what do we know about this? That this is definitely smaller than, like L is definitely smaller than all the x's, right? Because this is, we discussed about it, right? And we know that epsilon is greater than this, right? So we can write that L minus P minus A, right? Also, okay. And what is this epsilon equal to? Right? L minus M, which is M. We are saying that A naught is greater than this M. So this can't be an upper bound, right? So we got a contradiction here. But the thing is, we have taken only one case here. What about the other case, where it keeps dipping? We will discuss that now. Okay, so the thing about this is, if the sequence stops dropping at some point, you can just take that n and repeat the same argument, right? The only issue, the only time we only get the issue is that it is, imagine if it keeps decreasing, right? Because if it, we'll just find some n if it stopped dropping. We'll find some n and we'll repeat the same argument. But if that doesn't happen, then we have the issue. So we're going to say that this thing just keeps happening, right? So that is okay. Now, so can I write it something like this? Okay. Now, if we apply the limit here, what we'll get is this will go towards L, right? And if this goes to infinity, we'll get something like this, right?
You have taken the limit on K.
Yeah. Yeah, I should mention it. But the thing about this dropping thing is, if it is happening here, it is also happening before that as well, because we took a non-increasing sequence, right? So what we can say is, this holds for like n is equal to 1, right? So this will be B, right? And what is this equal to? A, right? Now what we have taken is M is less than L and L is equal to A, right? So M is less than A, and this A is an element that is inside the subset that we have taken. So again, we got a contradiction, right? This proves that L is the least upper bound. Okay. So what we have done here is we have used Cauchy criteria and sometimes we have used Archimedean property to show that axiom of completeness can be true. And like we can take any one of them to be axiom, basically. Okay. What I'm trying to say here is if we had an ordered field, and instead of this thing to be the axiom, we just have taken this thing or this thing or this thing and developed a theory, the entire thing would be developed easily. Like there won't be any issues, right? Because all of them are equivalent at the end of it. So this notion of completeness can be expressed by anyone. In the end, all roads lead to the Supreme. Yeah, that's it. Thank you.